Welcome to Embedded. I'm Alicia White here with Christopher White. We are pleased to welcome Nadia Peak to the show to talk about building things that build things.
Hi, Nadia. Welcome to the show.
Hi. Hi, Chris. Hi, Alicia.
Could you tell us about yourself?
Yeah. I'm Nadia Peak. I just defended my PhD at MIT in the Center for Bits and Atoms. The title was Making Machines That Make Object-Oriented Hardware Meets Object-Oriented Software. It was mostly about designing infrastructure for machine building. And I work a lot in the Fab Lab network. I've set up many, many Fab Labs. And as part of that, I guess, assembled many, many shopbots. And I also spend a lot of time just in the basement by myself at MIT. So the two extremes are a nice contrast.
Because the Fab Labs are going to have you interact with so many people as you get them set up.
Yeah, I think that's the fun part of it. I like to think of Fab Labs kind of like libraries. Like you go there and you have access to digital fabrication tools as opposed to books. And it's nice because if you go to a Fab Lab and you don't otherwise have access to digital fabrication tools at home, you can still share them. But it does mean that you have to engage with lots and lots of other people. And
Fab Labs is a particular name. I mean, we have tech shops and like the Supply Frame Design Lab we talked about a few weeks ago.
And other hackerspaces.
And various other hackerspaces. But Fab Labs is one particular type.
So I've set up a lot of Fab Labs, and Fab Labs share a charter for how they operate, and everyone has their own model, and so makerspaces and tech shops, everyone has a model of how to sustain yourself and how to provide access. And in Fab Labs, it's just a specific set of things that they all share. Like they're open 2 days a week. To the public for free, and they generally have the same basic set of machine capabilities. We have a shared inventory across them, but I've also set up I've also helped set up maker spaces that specifically don't identify as Fab Labs because they were unable, for example, to be open 2 days a week to the general public because they were in a university or something, and so they could be open to the students, but they can't be open to everyone. So yeah, I think that the more we can get of tech shops, maker spaces, hacker spaces, Fab Labs, the better. So there's no need to put too fine a line on distinguishing between them.
Okay. Well, we will talk a little bit more about that, but a lot more about your PhD thesis, I think. Before that, we're going to do lightning round. Have you considered adding a sound effect to that? You know, the lightning. Anyway, lightning round.
Consider it done.
I can make some noises. Pew, pew.
We're going to ask you some questions, and we want short answers. And if we are behaving ourselves, we won't ask for explanation. Okay. That sometimes happens. This is going to be a bit of a long one because we have a listener, Bruce, who added some extra questions specifically for you.
Ooh.
Christopher?
All right. We'll start with the usual one. Favorite electrical component?
I like the Allegra 4983 stepper motor controller a lot.
It's very specific.
It is. It's
much,
nice.
Much better than capacitor.
What is your least favorite component?
Well, I really dislike the 3482, I think, the same, also an Allegra stepper motor driver that keeps blowing up. So maybe that's why I have extreme opinions about them both, because one would blow up all the time and the other one never blows up. So
okay, how about favorite fictional robot?
Wally.
Cool.
Favorite type of actual robot?
Atlas.
What's Atlas?
Atlas is Boston Dynamics humanoid robot.
Oh.
Atlas is kind of scary.
Yeah, that's the one they beat up with the broomstick.
Yeah.
Okay.
But he can get up from the ground. That's very cool.
Yes, after he's beaten.
Yeah.
He comes after you.
I guess, well, a lot of the robots that I want to think are really cool. You know that, I don't know what this robot is called, but I think maybe it was Mitsubishi or Toyota is making a robot that bathes elderly people. But I think it was all concept art. I don't think it was actually ready yet. So once we have a robot that bathes elderly people, that would be my favorite robot.
Yeah, they do have the robot harp seal that acts as a pet and monitor for elderly in Japan.
Yeah, I think we're going to need a lot more of those kinds of caretakers soon.
Okay, next question. Additive or subtractive manufacturing techniques?
Well, as I will maybe elaborate on later in the show, I think that automation kind of makes the question additive versus subtractive unnecessary. But if I really had to choose one, I would go with subtractive.
Yeah, that's more fun.
It's also more precise.
Stepper or servo?
Well, depends on the load, I guess. Do you expect to miss steps? I'm going to go with steppers. Servos are often overpriced. I don't like paying too much for stuff.
Science, technology, engineering, or math?
Technology.
If you have to choose one direction, would you design a system?
The band?
No.
Sorry.
No. If you had to
I would
choose
definitely not choose the band.
One pathway, would you design a system that is more flexible for an expert user or one that is easier for a newcomer to learn?
Are those things mutually exclusive?
Usually, given a limited amount of time, you have to choose one.
I would go with the expert user.
What machine tool would you take with you to a deserted island? What good is that going to do you?
No, it specifies with three-phase power and endless feedstock.
Okay. So
that was part of the question.
So you're on a desert island that has nothing but three-phase power and endless feedstock. What machine tool would you take with you?
Cincinnati Hydrotel.
You're going to have to tell me what that is.
Is that a water jet?
Oh, no, it's a mill.
Oh, okay.
It's a really, really old mill from the 50s. I bet it wouldn't break down on a desert island.
So I have to ask now what you're going to mill on the desert island.
Well, you said I have endless feedstock.
Yeah.
So I'm just going to take it from there.
Okay.
Favorite physical constant?
I don't know. No favorite physical constant. Maybe Coulomb. Can we call that a constant?
Charge value? Sure. Oh, I'm lost now. That wasn't in the list.
It was in the list.
Which is most important to your job? Whiteboard, soldering iron, or keyboard and mouse?
I use a keyboard and mouse almost. I mean, soldering iron is pretty important. Whiteboard, not very important. But keyboard and mouse use quite a bit. I don't need really the mouse, just the keyboard.
Yeah. Yeah, he added mouse. I'm not so sure about that. When you were young, what did you want to be when you grew up?
I think I wanted to, I wanted to be a popsicle inventor.
I thought you were just going to say popsicle.
I want to be a popsicle.
I have a very detailed notebook full of popsicles that I was going to make. I think when I got a bit older, I think I wanted to be a chemist. So that changed a lot. I don't know if I have a good answer for that.
One of the people in our graduating college classes ended up as a math professor, and he started a popsicle business.
He does. He has a weird popsicle business.
So there's still hope. You can still do it.
Oh, yeah.
A friend of mine also just started a popsicle business. She picks up kind of fruit that no longer is beautiful enough to be sold and makes it into popsicles.
Okay, bits or atoms?
Atoms.
Is this exactly like your PhD defense went?
No.
That's too bad.
Is this harder? You can tell us. We understand.
It's much harder. Although I did have a really long question that was about security, trustworthiness, privacy, and ended with vis-a-vis Pokemon Go. That was a hard question.
Anything that ends with Pokemon Go.
Pretty hard.
Okay, I think that's enough for lightning round. I do sometimes ask making or engineering as part of that, but it's a longer question for you. So let's take it as a longer question. What are you more interested in for your career, making or engineering?
I guess I'm not, or as indicated by my past, I think I'm not totally sure what the difference is. But I'm going to go with making. I think I like the sound of that better.
You did just defend your PhD thesis. Do you already have results from that, or is it?
Yeah, I am provisionally Dr. Peak as long as I, actually submit my dissertation. I think it's all going to be swell.
Well, that's great. Congratulations.
Thank you.
Do you know what's next for you?
Yeah, I still work here. I am not switching desks or anything.
Cool. And there is the MIT Center for Bits and Atoms.
Yep, I'm in the Center for Bits and Atoms.
Although now that we know that you're biased for atoms, I'm not so sure they're going to keep you.
She can break it off as a splinter group.
They have space for both types here, bit people and atom people.
And bits don't take up a lot of space.
Yeah, they all sit upstairs and atom people sit downstairs. Makes sense.
The site says it studies how to turn data into things and things into data.
Yeah, that's a pretty... Or I guess it's a poetic way of putting what we... I mean, I think there are many levels in which we do that. There is... if you think of programming a machine tool to make a thing, you can think about that being turning data into stuff. And if you think about going from... so one of the research projects that's pretty big here is one of digital materials. So instead of, for example, additively manufacturing by squeezing out hot plastic or curing resin, you assemble parts out of, say, tiny Lego. And so there you're programming a material that is being assembled out of tiny Lego. Or maybe programs can be put into materials. Those are all things that people work on here. How can you, one of the Center for Bits and Atoms students, Noah Giacomo, he's working on using DNA as a kind of storage media. So instead of, since we can now make our own DNA, why wouldn't you just want to back up your computer in DNA? It's really small, very portable. So yeah, there's all kinds of different ways in which you can interpret how the Center for Bits and Atoms works on going from data into things and things back into data.
And for you in particular, it has to do with building machines that can build things. Is that right?
Yep. So I build machines that are computer controlled or even controlled by things that are maybe don't entirely qualify as a computer.
Oh, I understand that. I often say I write software for things that aren't computers.
Yeah.
So I get that. And your PhD dissertation was making machines that make object-oriented hardware meets object-oriented software. What does object-oriented mean in those contexts?
Well, I borrowed heavily from the paradigm of object-oriented programming to understand how we can make it as easy as possible to build up machines. And so if you think of a mechanical component of a machine being an object that has state, so it has data, it has position, and it might have a method as well, like you could make it move back and forth. And you also think of a software object that maybe can control or can request new position. You can think of those as two different objects that can pass messages between each other. And if we wanted to add a couple more objects, like more motion stages to build up a more complicated machine, then you can think of an assembly of objects that together form a machine with an end effector and some interface, and then an infrastructure of objects that makes the machine, which makes the machine easier to reconfigure or maybe easier to make application specific. The other thing I borrowed from, the other paradigm I used heavily was the end-to-end principles for networking, where in the early days of the internet, some smart people, including David Clark and David Reed and Vint Cerf, argued that you shouldn't implement too much in the network itself. Because, for example, if you wanted to check if your data had been corrupted in the middle of the network, it could still get corrupted again later. So all the things that are specific to the application should be implemented at the endpoints, and everything in between should just be as simple as possible shared infrastructure. So you have machine objects, in my case, you have machine objects that you can then assemble together to make a machine platform that you put an end effector on and a software interface into, so that you can have an application-specific machine.
How does this differ from modularity?
It is modularity. It's I could also call it making modular machines that make, or it's I think that the reason I used object-oriented programming as a metaphor was because I don't necessarily just want to connect everything in one like connection point. The way that if you have like a modular mechanical kit that you can snap together and distributed controls that you can also connect together, but they don't necessarily. Then you have to connect the control system to the mechanical system and the mechanical system to the software system. You still end up with these kind of choke points in between the different layers of description. So I'm trying to avoid that by saying, well, this control node goes specifically with this machine node. But I mean, you could call that modular too.
It's also kind of a distributed system, right? You've distributed the controls throughout the modules rather than having a central brain.
Modular, distributed. Yeah, there's many words to choose from, I guess. But yeah, I generally call them distributed network controls, but I don't know if it would make that, if you said distributed mechanical system, I don't know if that would just make me seem crazy.
Not to us.
Okay, well, we can call it all the things. Distributed, modular, networked, object-oriented assembly of things to make machines.
One of the difficulties of modular hardware is that it tends to be more expensive. I mean, the connectors alone aren't cheap.
Yeah, that's true. It's so one thing that, especially in machine building, MIT has a very large mechanical engineering department. And one of the ways that I explain to them why I'm breaking up machines into all these different parts where connections have opportunity to fail, it's never going to be as good as something that's purpose built. And so sometimes I try to bring up the analogy of packet switching networks. Packet switching networks were sort of ridiculed when they first came out because people were like, this is a really strange way to try to transmit data from point A to point B. It would be much better just to have a dedicated line. And at the time, no one imagined that there was going to be the internet and like there were going to be millions and millions of connections. It was just like, so you want to like connect Stanford to MIT? Like, why don't we just put a wire? And so I think that the unanticipated applications that you can build using modular components make it worthwhile to it's definitely a trade-off, right? Like, yes, it's going to be less optimal and the connections might fail. But instead of you having to design a machine, or in this case, instead of you having to design a machine and spend maybe, like, say you were pretty fast at it, like say you have in a week you can build a custom machine to do something, it's still not going to compete with like in a few hours or even maybe minutes, you can put together a bunch of modules and start your automation process. And so I think it's more of a, how do you go from no machine to your first machine, rather than going from your first machine to a better machine. Maybe by then you should, if you wanted to make the same machine over and over again, you want to reduce costs by removing connectors, maybe make your structural loops smaller. Maybe, there's a lot of ways that you could optimize something. But if the problem is that you haven't automated it at all yet, or you don't have access to that computer controlled precision yet, then having the drawback of having connections which might fail seems worthwhile. It definitely worked out in the case of TCP/IP. So maybe we could take advantage of that.
Well, like object-oriented modularity is something we often recognize as good in software. And in hardware, I would think it is also very good. I certainly appreciate all of the breakout boards that exist and the eval boards and the dev kits so that I don't have to design a board for everything.
Yeah, definitely.
So that makes a lot of sense. But there is a downside to it. And it's good to hear that sometimes you make a different decision. Have you been very successful in putting out modular systems that are buildable by other people?
Yes, I would say so. So one of the machines that I built a long time ago is maybe 2012, 2011, together with Jonathan Ward, who now works at Shopbot, was a small plastic milling machine. It was like made out of cutting boards, and it was for milling circuit boards. And it was like a small, cute mill, and the cutting boards, the HDPE cutting boards that we bought come in all these different colors for restaurants, and it was like cute. And we made it open source so anyone could make it. And we thought, everyone is going to make our milling machine, almost no one made it. It was really, you needed access to a big mill to cut out the parts. And then you needed to follow our assembly instructions, which were written for people, or like it was hard for us to write assembly instruction, I think, without watching. We should have watched someone who had never put together a machine and written instruction based on that or something. I don't know. I don't know why the documentation was not clear enough. It never ended up working well. And so that's one of the reasons I think that I started working on this much more modular approach. And so I built a bunch of modular machine components. We use sheet metal or aluminum, folded aluminum stages, and milled aluminum rotary stages, and distributed control systems to go along with that. But those were not necessarily that accessible because you needed those parts to build them. And so James Coleman and I made a different version of it that was made out of cardboard. And the cardboard machine kit, the cardboard machine kit was really pretty successful because it turned out everyone was comfortable cutting. Even people that didn't have laser cutters and didn't use the laser cut files were still able to make the cardboard stages. It was very easy for people to build kind of a minimal viable machine and then optimize after that. And so even though the cardboard machine and the cardboard machine kit and the parts that went into the MTM Snap, they're kind of comparable in price. I think the MTM Snap had a bill of materials of about $350. And if you want to use, say, 4 linear cardboard axes, that would probably be around $250 or something like that. Together with the electronics and together with the electronics and all of the hardware and stuff that you would need. It was just much easier for people to make the cardboard machine, and then also to iterate on it. Once they made machine 1, they were like, okay, actually we want not to have a pen plotter, but we want a milling machine. So we're going to attach a spindle now, or, just like the modifiability was very successful. So far, I think about 200 of those cardboard machines were made. And as far as I know, only maybe 10 MTM Snaps were made. So we're making progress.
When cardboard has a pretty low barrier to entry, I don't feel bad if I destroy cardboard.
I was going to say, yeah.
But if I had to throw away even plastic, even
or
like
aluminum,
you were saying, throwing away aluminum would be very hard. But even the cutting board plastic, I still would feel odd.
Yeah.
But cardboard, sure, that comes in and out of my life so fast, I don't care.
Yeah, everyone is used to it as a strong, lightweight packing material, right? So it's readily available. We use the cardboard, or specifically for this machine design, we use the cardboard that you buy for science fairs, like the trifold poster board, and it comes in different colors. I'm obviously very focused on things coming in different colors. And it fits, so one linear stage fits exactly on one trifold poster board. And so then it makes it easy for people to find the same cardboard. But even if they didn't, it wouldn't matter because the cut file for it is parametric. So you can adjust it for different thicknesses of cardboard or sizes of stage.
So many of these tools start with a stage. I mean, if you talk about a laser cutter, you are talking about a laser on 2 stages, maybe 3.
Yep.
And if you are talking about a 3D printer, again, you're a couple of stages.
Yep. Yeah, people made cardboard laser cutters. That was terrifying.
Talk about chopping off your own foot there. There's all kinds of things.
So I was like, kind of like, yeah, you guys, like, good show, good work, great work, but maybe think about this. They're like, it works great. We don't know. I'm like, the cardboard isn't underneath the laser, Nadia. And I'm like, okay.
And milling machines, CNC milling machines are, of course, stages. So you have those and the plotters, again, stages. Now, many of those need some sort of spindle thing, mostly for milling, I guess is where the spindle comes in. Mm-hmm. What other modules have you made and put out in the world?
Well, so I'm working currently on like an end effector kit. I've built a bunch of different end effectors that so the cardboard stage has these 4 little nubby things on it, kind of like Lego, so that you can stick them onto each other into different configurations. So say you wanted 2 axes, you just stick them on top of each other and they can move around. But the nubby thing also accepts, for example, an end effector. So James and I built plotter end effector, 3D printer end effector, syringe end effector, microscope for, gigapan.
Well, syringe would be really useful for chemistry. If you do little tiny micro stages, and you can do a whole bunch of experiments at once. Sorry, he was wincing.
I'm imagining the robot in Star Wars with the syringe on it. Never mind. Go
on. James used a version of the syringe robot to decorate a birthday cake for me once, so that it's like you can think about scary syringes or syringes that give you cake. It's very precisely decorated cakes, good for everyone.
This could really work back into popsicles.
Yeah. See, like all this buildup, and in the end, I'm going to be a popsicle inventor. Have I put other end effectors on these machines? Oh yeah, knives for swindle knives, swivel knives. I mean, I don't know what other end effectors. I mean, sometimes what you want to do is polishing, but that wasn't really a different end effector. We just put a polishing sponge on the end of our spindle because we're questionable engineers. But yeah, I think that making it easier for people to put different end effectors on the cardboard stages would be a great kind of next addition to the kit. Because right now, a lot of people have made hot wire cutters with the stages because you don't really need to do any kind of end effector control for that. But so I use the distributed network controls that use a library called PyGestalt that was originally invented by Ilan Moyer, and I contribute boards to that, or different boards to control different things, library. And so I think if it were easier for people to get different boards to control other things, not just extruders or stepper motors, but can they attach different kinds of feedback loops, then that would be an easy way to get people to be able to more easily make more machines.
And so that actually comes to the next question I had for you, which was about software. It is all well and good to make a stage and make some motors go back and forth and put an end effector on so that they do different things as they go back and forth. But how do you control all this?
Great question. I think of the software interface as often one of the endpoints of the network. And there are a lot of different ways that you can control things. Like people who listen to podcasts about embedded hardware might have heard me complain about G-code extensively on a different podcast. And that is definitely one way that you can control a machine. You can take a design file and run it through a processor that will be able to generate a toolpath based on the object that you want to be fabricating. And that toolpath consists of coordinates, or like places that the machine needs to visit. And then you stream that file to the machine. And that works really well for lots of machines, like milling machines or laser cutters. They can all operate well on just moving this following pattern. But I'm also interested in other kinds of software, hardware feedback loops. So, for example, one that I use is putting a video camera on the machine so that it will behave differently based on what it sees. So if, for example, you're pipetting something into a Petri dish and you want to pipette until the Petri dish colors from blue to pink, then how do you write a control system for that process? And so to be able to do that, with my advisor, Neil Gershenfeld, I've been developing kind of a workflow composition tool that runs in browser called mods for modules. See, we like modularity. And mods, you can, it's all JavaScript. It took me a while to get used to writing JavaScript because it's all high level and crazy. But you have different modules that you can connect together, like you might do in Simulink or LabVIEW or Grasshopper. And you can write modules that you can also put in. So, for example, if you wanted to do like a standard 3D print toolpath, you could import an STL and then slice that into a toolpath, generate coordinates, and then export it to a machine. And to be able to do that part, we're using we use a virtual machine to talk to the distributed control network. And this is kind of a confusing use of the word virtual machine. It's not like a actual virtual machine, but it's the machine. It's a description that explains which of the distributed control nodes do which part of the work in the machine. So if you had two stages, X and Y, then there would be one control node that's moving the X motor and one control node that's moving the Y motor. But if you used, for example, a HBOT configuration, which is now in a lot of 3D printers, then moving the A motor moves the stage in both X and Y directions. So you need to move the A and the B motor just to be able to move X, and the A and the B motor just to move Y. And so the thing that translates from how does the machine need to move to what are the motor commands that need to be executed is the virtual machine in this case. And so from the mods environment, which runs in the browser, there is a WebSocket connection to a Node.js server that then communicates with the machine over. Most of them run RS-485. That's a part of the system that I don't like as much because I would prefer not one choke point of connection, but I'm working on that. So for now, you could, for example, put through a 3D print toolpath that way. Or we also have you can import an image and then do a threshold on that image, then vectorize that, or like do edge detection and vectorize that image, and then take those vectors as a toolpath for example, a milling machine. And it also has a video input, so that you can compose all of these different programs out of modules or write other modules. Like Gphoto 2, the photo library that allows you to control a lot of different kinds of cameras remotely. If you wanted to remote image capture is one of the modules. So this is kind of like a software composition framework for writing, for automating actions on your machines. And that hasn't been as widely used yet because I think it is not as well documented as it needs to be. And I'm also working on that. But if you want to test it, you can test it at mods.cba, Center for Bits and Atoms, .mit.edu.
Mods.cba.mit. mit.edu. Put that in the show notes.
Cool.
I'm using it right now.
That is not a friendly landing page, but we'll talk about that later.
Yeah, see, these are problems you have when you don't interact with enough people.
I know that MIT is also doing that thing, Beetle Blocks, which is sort of a CAD program. Are you familiar with that?
Never heard of it. I want to look it up after this. Sounds awesome.
You mentioned, I think, Eric Rosenbaum, and he was one of the people on that. They're calling it Scratch, similar. And
for CAD,
very cool.
That's awesome. Eric Rosenbaum is very cool. Also known for the Makey.
Ah, yes. Okay, so I'm not going to ask you about Beetle Blocks. Let's just cross all those questions off. And all of these things that you're talking about, building quickly and building simply and making modular, all these things. You're talking about building tools. You're not talking about building things. You're not talking about my next TV or my next cell phone. You're building the tools and not the end products.
Yeah. So I think it is hard to anticipate what the infrastructure is you might need to make a thing. So, for example, a 3D printer is considered to be like a universal thing, right? Like a 3D printer can make almost anything. Except in reality, like a 3D printer can't make very many things. 3D printer can make kind of smallish things, mostly plastic. And so what if I wanted like a coil? What if I needed to wind a coil for a solenoid and it needed to be like of specific resistance? If I had a bunch of different modules that I could assemble to be a coil winder, then I could have a kind of precise computer-controlled process. And after I made the coils I needed, I could reuse those parts in other places. Or if I wanted to mill a part that was very long and skinny, then I might not have access to a laser cutter of that particular size, but if it was easy for me to assemble different modules with that work volume, I could do that. James, who I built a lot of the cardboard machine kit with, James Coleman, he works at Zahner Architectural Metals now, and they do they do a lot of the sheet metal fabrication for buildings like the Walt Disney Concert Hall or the Stata Center at MIT, Gary Building, both Gary buildings, or the Peterson Automotive Museum. And so they make 100,000 parts for any given building, and 10,000 of them are unique, or 10,000 unique styles, or 10,000 unique designs. And so for them, they have to they either have to have like the biggest water jets, or that they can. But even then, it's hard to make. It's hard to make things that are that unique and still have an unreconfigurable shop space. And so I guess I used to think that the things were the application, like you were mentioning. Like, why am I not talking about the things that you can make with machines? But I have since then started to couple the machine and the thing together in the application. So I think that to make a thing, you need a machine. You don't always need a machine. Maybe it's a very simple thing and you don't need computer control. But for a lot of things, to be able to make things that are complex or precise, you want to have some level of precision in its control system. So then I couple the machine with the thing. And so I'm thinking a lot about how to making the machine part easier, because right now I think making the machine is kind of hard.
Machines have gotten so much more accessible. My shop in college years ago was wood and then metals and then aluminum. And I loved the shop and it was amazing. But I always knew that I couldn't do it at home. And then it wasn't that much longer before I started to see these tools where I could start to do some of them at home. Not just a saw, and not even just a table saw that was home ready. More, we just got a 3D printer. We have a laser cutter on order, and we have all of these neat tools that I couldn't imagine. And I know places I can go to get milling machines, and I look at the other mill and I drool every single time. So I think about all the things you can
other mill,
build.
Semi-based on the MTM Snap.
So these tools have gotten a lot more accessible, as well as the idea of these tool co-ops like the Fab Labs and the makerspaces. Do you see this continuing? Do you see everybody having their own set of tools?
Well, I think that's one way that you can think of how these things might progress. Lucy Suchman is a anthropologist who used to work at Xerox PARC. And she worked at Xerox PARC at the time when they first decided that copy machines were no longer going to be something that required dedicated technical staff, but was going to be something that offices could have, and any user could go up and use them. And so they had all these, this is like 1985. So they had all this advertising, Xerox did at the time, where you're like, it's just a big green button, go press the big green button. But the experience that a lot of people had when they walked up to a photocopier was one of sheer rage and upsetness. And so Lucy studied that experience, like what is the experience that people have when they go up to a copier, and then conclude that it's unusable. And she wrote that up in her dissertation and later turned into a book called Plans and Situated Actions. And so a plan is like you go up to a copier and you use it for its intended purpose. So you photocopy one-sided or you photocopy two-sided. And maybe a machine has a bunch of different plans, like photocopying one-sided or photocopying two-sided. But then there's also all kinds of contextual information that you as a person have, like how is your action situated within a context? And a lot of machines do very poorly with that, especially the Xerox machine at the time apparently did very poorly with adapting to situated knowledge of humans. And her work was of great influence to me because Lucy Suchman is credited with having invented human-computer interaction by studying people interacting with photocopiers and then stating that doing an ethnography of user experience is something that would probably be pretty useful for companies that were making machines. And that totally changed how companies like Xerox or other companies like Nokia, they regularly now employ anthropologists and ethnographers to figure out how to make something easier to use. But plans, I think, are a good way. Plans are a good kind of crutch, or it's a good way. It's very easy for me to walk up to a 3D printer and 3D print something off of Thingiverse, for example. This is a very well scripted user experience. Or if I want to go up to a laser cutter and cut something out there. But each one of these user experiences is very well tailored. Like if I walk up to a Form 1 and I press its big glowing button, it's all, people think about what you're doing there. But I do often feel like it's not all of the ways in which you veer off script, all of the ways in which you leave the plan, those are still not totally, they're not totally well developed. So if you wanted to use your Shopbot for assembling giant Lego instead of using it for milling, you might run into a lot of hiccups, even though, like we discussed earlier, they're just a bunch of stages. And so I think that, yes, as market demand increases, we're going to see way better user experiences in lots of different kinds of digital fabrication machines, bringing them into homes or shared maker spaces and making them more accessible by making them cheaper or by making them more user-friendly. But I don't think that that's enough, because I don't think that we can imagine all of the things that people might need the precision and accuracy of computer for control for and turn them into products. I think that people are more inventive and need more flexible tools than that.
Well, and beyond the tools, I think the other barrier is ease of design, because right now for things like 3D objects, there's a pretty big learning curve for Okay, how do I learn to do CAD? Well, you go.
Here's a week-long tutorial.
You go to DeVry and you get a certificate. Whereas, certain other things are not so impossible. Like if you get a laser cutter, okay, and you're doing outlines, anybody can draw.
Yeah.
So that's another axis I think that's that needs addressing too. Is okay, we have these machines, they're cheap, anybody can use them, but if you're just downloading something from Thingiverse.
Yeah, kind of the amazing thing about digital fabrication is also that, software is kind of the most rapid. If you wanted to iterate on some engineering process, software is very easy to run or to write and then figure out what's wrong with it and then write another iteration of. But in machine tools, the software seems to get like the least amount of attention in terms of upgrades that you can get in a machine. We have a Sodic wire EDM, and the software is absolutely incredible. Like you can only give it file names with uppercase alphabet characters.
That wasn't a great incredible.
No, it's like terrible. It's like it's incredibly bad. The file names can't be longer than 6 characters, but it doesn't say that anywhere. So if you have a file name that's longer than 6 characters, it just kind of silently fails. But they did upgrade, they upgraded the panel with which you can look at their software that looks like it was designed in 1987. It's like a touch screen, and you can squeeze pinch it, and there's different parts of the touchscreen that you can touch, and there's also a keypad, and there's all these other parts. But the software itself is incredibly, incredibly bad. And in terms of ways in which they, as a machine tool company, could improve the user experience, writing better software seems like a pretty cheap and easy way to do that on already existing machines. But it's just not one of the iterations that seems to happen a lot. And I think it's partially because the system integration going from the software interface into all of the different parts of the machine is complex enough that you can't just kind of write a script for it. So instead you have, or I have a better example, Epilogue laser cutters. I hope they don't get mad at me for saying this. I don't think they will.
I was about to pick on them, so go ahead.
So Epilogue laser cutters. So for the tools in the Fab Lab includes laser cutters and milling machines. We have this software that we write called the Fab modules. Different than mods, but also modular. And the Fab modules is like an easy tool pathing program for lots of different machines. You can also do some rudimentary design in it, but mostly it's for tool pathing. So you start from a PNG, and the PNG then can be exported to a milling tool path or a laser cutting tool path or a water jet cutting tool path. And so the idea is that you don't have to learn lots of different kinds of CAM packages to be able to use the different tools in the Fab Lab. And so the Epilogue file format, we needed that to be able to talk from the Fab modules to the Epilogue. And so, we print it. So when you're sending it from a Windows machine, an Epilogue file, we printed that to file instead of exporting it out over the USB cable and looked at it. And the end of the file has 10,000 spaces in it. And then we're like, well, maybe that was an accident. So we removed the 10,000 spaces and tried to send it from the Fab modules, and it didn't work. It needs the 10,000 spaces. And then after having run Epilogue, and so we just added them in, okay, so we put in 10,000 spaces if that's what it needs. And at some point we actually talked to an Epilogue engineer, and we were like, what's up with these 10,000 spaces? What's going on with this file format? We don't really understand. I mean, we were able to use it, but we don't really understand it. And the Epilogue engineer was like, yeah, the guy who wrote that software retired a long time ago, and no one really knows how to modify it. So we just put the 10,000 spaces in too. And I was like, this is incredible. This is completely ridiculous. But it's just that's the way that people are used to kind of having to have this technician attitude when dealing with machine tools. And so this kind of craziness at the software level seems to be, unfortunately, not uncommon.
Well, and it can become a point of pride. Oh, I know how to use this machine. It's really complicated.
Yeah. I think it definitely
but
is.
But it's totally pointless. I mean, you don't actually know how to do anything. You're just interacting with the idiosyncrasies of something that's badly designed. Yeah.
You've been programmed by the machine, or as Lucy Suchman would say, you're exactly following their plan, or you've conformed to their plan, and it doesn't accept your situated action. I think that attitude, I think, is something that I don't know exactly how to address that in maker spaces or hacker spaces or fab labs, but this attitude of like eliteness or like being good at something, a lot of it has to do with this invisible knowledge. Like, how do you transform, like how do you go from RML to G code, or like how do you export something from Illustrator so it can be seen by this laser cutter, all of this kind of invisible expertise. And once you know it, it's like, then you become good at using a tool, and that makes you feel good. But it would be better if once you know it, you could fix it so it's easier for everyone else. I don't know. This is something I think about a lot. How do we make it so that it is not cool to know things that other people don't know? Instead, make it cool to make it really easy for everybody else not to have to know those things.
Well, there's a process here. You find out that you need 10,000 spaces. You push back on the manufacturer. The manufacturer refuses to do anything. You document it so other people know it. And then you build a tool that eats the manufacturer's lunch, because clearly they were too stupid to survive.
Yeah. We're working on it, I guess.
And we are. I mean, there are so many lower cost tools than there used to be. And many of them are recognizing that the software needs to be more accessible, more modifiable.
It doesn't have to be baby software, but having it be unnecessarily complex or technical.
With your new 3D printer that was super cheap, you just picked up PID tunings off the web. We talked about tuning it ourselves, but in the end, you just loaded stuff that worked a lot better than the manufacturer had.
Right.
And that sort of sharing of knowledge is important for everybody.
Or it could just work right out of the box.
Well, that would be optimal, but that's never going to happen for everybody.
Right.
Having it work out of the box in a situation where we have to ship things is really hard, sadly.
And you never really know exactly what context things are going to be in, right? Like, one thing that I think is kind of funny is if you ride the subway in New York and there's no cell reception, you have all these people who use Apple phones who get frustrated because a lot of the phone functionality relies on persistent network connectivity. You think that they would consider New York City as a major use case of Apple iPhones. But it's kind of like, it's just not a situation that was imagined by the designers. And then the end users have very little control over how to modify the tools that they're using. And so I think it would be better to build in more end user control or more access for end user control rather than trying to anticipate in advance all the possible things that your machine might need to cater to.
But then that edges back toward being an expert technician to be able to use your machine.
Yeah, sometimes I just want my phone to be a phone, damn it.
Yeah, I think that there is a way in which you can have
both, yeah.
Both. Like, I think there's a way in which you can modify things. Like, maybe they work one way that works for most people out of the box, but afterwards you can still change a lot of stuff. And I think that the challenge to changing things like cell phones, for example, is large enough that a lot of people don't do it. Yes. I suffer immensely because I run CyanogenMod. It's so annoying. Half the time, I'm like, I'm sorry, I can't hang out with you. I have to rebuild my phone's OS.
I used to work on that.
Oh, really? That's awesome. Thanks for your service.
Sort of, kind of.
So going back to personal fabrication machines, which someday we're going to start calling replicators, but not yet because they don't deserve it yet.
Yeah.
They don't often match the precision and the availabilities of those things you can find in a good makerspace or at a university or at a shop, like a real shop. The industrial machine tools, I mean. How much of closing the gap between personal and small fabrication and getting to those great industrial machine tools is a matter of engineering, and how much of it is a matter of science?
Well, I would disagree with that somewhat, first of all. I don't necessarily think that using small modular machine tools gives you less precision than other machine tools. Because, for example, if you wanted to mill, like one of the machines that one of the Fab Labs made is this tube cutter. It cuts PVC pipes so that you can join them together at different angles. And so you need to have precision milling, but the work envelope that they made is like very small and tailored specifically towards PVC pipe of maybe 2 inches in diameter. And so you can have local precision and have it actually work much better than if you wanted to cut like a catenary curve onto a piece of PVC pipe with this like standard mill. It would be complicated to program in and complicated to kind of execute on. And so I don't entirely agree with the fact or like the assertion that industrial machine tools are better than the machine tools that you can make yourself. And so I think that maybe there are certain things that are too expensive to expect people to have access to at a personal scale. So maybe we're not going to make 36 by 18 foot gantries for people to make things out of. But maybe there are other ways.
Concrete printer. I need a 3D concrete printer.
Yeah. But there may be other ways that you can achieve that kind of motion. Like instead of trying to make a gigantic gantry, maybe you can do it with haspels and do positioning with like a 3-tendon kinematic structure instead. You just like hang a bunch of pulleys in trees and like hang your extruder in the middle and go from there. And so I think that as far as I'm concerned, I hope that the tools that we use to make tools become much better so that the tools that we need to travel to aren't as important anymore.
One of the things I've seen that you talk about is how being able to shift your tools around is important to a company's agility. Do you have anything particular to say about that?
Yeah, I mean, if you're a mass manufacturer and you're going to make the same object over and over again, then being able to move your stuff around or being able to reconfigure your machine is not that important. But if one day you're going to be making one thing and the next day you might be making something that has a very different geometry, then being able to reconfigure is very important. And so I think that makes a lot of sense if we're going to be producing, like agility at the production level makes a lot of sense if we're going to be working in low volume. And I personally think that working more in low volume is going to be much better because it will enable us to make products that are more locally specific, less transportation and kind of distribution objects problems. There's an argument to be made for never reconfiguring your shop floor because you're just going to be making the same parts over and over again. But I hope we're moving away from that scenario.
Is design for manufacturing still important for low-scale production? Low-volume production?
Design for manufacturing is important, but I don't think it's the only answer. If you want people to be able to scale up or scale down, then you need to also be able to have an agile manufacturing. You need agile manufacturing as well as designs that are well suited for the manufacturing process. So sometimes I like to say, yes, let's teach makers design for manufacturing so that they can manufacture. But at the same time, let's also work on changing manufacturing so that makers can more easily access it.
Okay. I wonder sometimes if production, like large-scale consumer-style production, is more like cloning, and this low-volume prototyping and agility is more like evolution, that you can go into niches, smaller niches, and be better adapted for them.
Yeah, that's a great metaphor. I like that a lot.
Feel free to use it.
Thanks.
The code, the bits and atoms part, the G code or whatever we're using to describe the thing we want, allows for more prototyping. But the tools, you've convinced me that they may not lack precision, but they do often need more maintenance. I didn't want a 3D printer for a long time because really I have enough pets and they tend to want some feeding and caring for. How are we going to build modular systems that are, how are we going to build systems that are modular, easy to use, easy to take care of, and inexpensive?
And 50 words or less.
Yeah. With a business plan, please.
Yeah. I mean, I think that all of these things are possible, but they're not, there's not some like, if only we did this, everything would be better answer I can give you right now. I think that making things easy to maintain, it just involves design iterations. And so I hope that lots of people will work on machine infrastructure so that it makes it easier for people to build machines out of that infrastructure. When we first started with packet switching networks, they also kind of sucked, but it's a little more robust now. And I think that the way to approach it is just iterate. And if it's too hard to iterate, well, then we need to change that first.
And that's what you're doing.
I'm trying.
Cool.
And it's not just me. Lots of people. With lots of...
Okay, I have a totally different set of things that I wanted to ask you about.
Yeah.
How was the process of getting a PhD at the MIT Center for Bits and Atoms?
Well, at MIT we have this acronym, IHTFP, which stands for, I hate this place. Or... alternatively, I have truly found paradise. And I think that both kind of apply. At MIT, you work really hard. Like you work really hard, you're expected to work really hard, and you're pushed really hard. And you just do an immense amount of work, more than you ever imagined that you could have done before. But at the end, I'm surrounded by excited people who are very bright and motivated. And I have all these resources that I can use, all these fancy industrial machines I can use, and yet I choose cardboard. And so I would say that it's been a really great experience for me. But I also see sometimes it can be really hard. Like MIT, like many other places, is a sexist place, and they're working on it, but they haven't solved those kinds of problems yet. MIT has like a lot of issues with dealing with like the group of people that you might expect to show up in an institution like that we don't necessarily all have the best social skills or the best ways of working together. But all in all, I would say that what you gain from it, or what you end up with at the end, like the friendships that you make and the work that you produce, it's the best thing ever. It's so great. I'm very happy.
This sounds like an ad for Real Genius.
I don't even know what that is.
It's a movie. You might want to watch it. It was pretty good.
It's very 80s.
It's a little dated now, but
it's still worth watching for people who went to engineering schools.
Does it have a T-shirt in it that says "I heart nuclear waste"?
It does. Toxic waste.
I heart toxic. Okay, someone else has told me to watch that movie. I'll have to watch it.
Was defending your thesis what you expected?
Yeah, more or less. Generally, I think like when you're allowed to set a date for your defense, and your committee says that they're going to come and all that, then by then you know that you're doing pretty well. Generally, if they don't think that you're
doing enough work, or if they don't think that you're going to pass, then they won't let you schedule a defense. And so getting to the part where you're giving the defense is already pretty good. Like there's a small chance you can still fail it, but by then, people are already vouching for you. And so I guess I walked into that room, and I laid out all of the machines I had made out on the table. So that was also kind of fun. There was a little mini exhibition, and this pop-up briefcase fabrication machine, and the snap, and all these metal stages, and all these, and so there was like a real progression. So, just having people come to the defense and seeing those things, that was already pretty fun. So the defense was less, and a lot of people who came to one of the things that I was surprised by, a lot of people came. It's like the middle of summer, and it was like in the afternoon on a Monday. But it was really, really busy. There were like lots and lots of people standing around. Like they couldn't sit down anymore. And so one of the things that was just kind of exciting was to be able to kind of tell a short version of the story of all of the things that I'd produced as part of my dissertation. So that was fun. But it wasn't like the word defense kind of seems like there also needs to be some offense that you're protecting yourself from, and it didn't feel that way at all. It was more, I got some questions which were kind of like, well, why this, or what are the implementation details of that, or how could you evaluate how students who engage with these kinds of tools would be more successful, but nothing like, wow, you reject your entire premise and all of this work sucks, so all in all, I would say it was a good experience, and I encourage anyone who is interested in doing a PhD to try to schedule your defense as far in advance as you possibly can, because professors are impossible to get into the same room.
Christopher has a good story about that.
Yeah, I had my master's oral exams. One of the people I scheduled didn't even show up. So I had to scramble.
That was my biggest fear.
Scramble through the department, finding somebody who would be willing to do it. Otherwise, I was going to have to do it some other time.
That was my biggest fear on Monday. I can't believe you actually went through that. That sounds terrible.
Yes. And the replacement had interesting questions.
Oh, no.
He was the one that asked you how many electrons
First question, how many electrons are in a chicken?
Yeah.
And I was like, what?
Weird.
Oh, God.
Let's assume a 10-kilogram chicken.
And it's spherical. And it's in a vacuum.
Frictionless.
All right. I think we have kept you for long enough. It has been wonderful to talk to you, but I hear you're getting on a plane soon.
Yeah, that's true. It's only tomorrow. Don't worry. I'm going to Shenzhen. I go there a lot to buy motors and other kinds of parts, but now I'm going there because I'm going to Fab 12, the 12th annual Fab Lab conference. It's going to be partially focused on Fab 2.0, which is using Fab Lab machines to make more Fab Lab machines. And so I guess I'm kind of in charge of that component. But it'll be pretty fun. Yeah, that's where I'm going next.
Cool. Christopher, do you have any other questions?
I had something about making machines, but she just said that's what she's going to Shenzhen to do. So apparently that's happening.
No. Using machines to make more machines.
Right. Yeah.
Not making machines that make machines by themselves.
Right.
No Skynet.
Wow. Okay.
Not yet. Soon, though. Soon. Nadia, do you have any last thoughts you'd like to leave us with?
Yeah. Last thoughts. One of the best things I think about working on projects like these has been that I work with people that have very different backgrounds from me, and I learn a lot from them. But you need to have kind of the space to be allowed to do that kind of interdisciplinary work. Or, if we had to really efficiently finish lots of projects, then I wouldn't be able to work with someone who didn't work in the same way as me. And so I guess final thought is, how can you encourage or give yourself space for those kinds of interdisciplinary collaborations? Because
for me, they've been really valuable, but they've also been a struggle. I'll get into big fights with James because he thinks that all of my graphics are terrible, and then you focus on that instead of doing next work. So how can you create space, especially for hardware? I think this is important because in hardware you tend to be hyper focused on something very specific, and so how can you see a bigger picture and encourage more kind of cross-disciplinary collaboration? It's something I think about. And so if people are listening to me anyway, then, maybe you're thinking about it too.
Seems like a good thing for us all to think about. My guest has been Nadia Peak, research scientist at the MIT Center for Bits and Atoms. Thank you so much for being here.
Thank you, Alicia. Thank you, Bruce. You guys have a great evening.
Huge thank you also to Bruce for suggesting Nadia as a guest. I heard her on the Amp Hour too and wanted to talk to her then. I'm happy he reminded me. Thank you also to Christopher for producing and co-hosting. And of course, thank you for listening. Hit the contact link or email show@embedded if you'd like to say hello. As usual, I do have a final thought to leave you with. This one from Maya Angelou. What you're supposed to do when you don't like a thing is change it. If you can't change it, change the way you think about it. Don't complain. Embedded FM is an independently produced radio show that focuses on the many aspects of engineering. It is a production of Logical Elegance, an embedded software consulting company in California. If there are advertisements in the show, we did not put them there and do not receive any revenue from them. At this time, our sole sponsor remains Logical Elegance.